Hello viewers, today I'm going to present my um, project work on thermomechanical simulation of friction welding of plastic materials. My name is Kazi MD Masambilla. I'm a graduate research assistant at WM Keck Center for 3D Innovation here at the University of Texas at El Paso, and I'm also a PhD student in Mechanical Engineering Department. So in today's presentation, I will talk about the motivation of this project, and then I will give the background of this project, and certainly I have some objectives for this project, and then I'll talk about the relevant geometry and boundary condition and what are the things I looked for the mesh optimizations. And lastly, lately in this presentation, I'll talk about the simulation discussion conclusion with the future works. So in the plastic welding technology, it has a really great potential in hybrid manufacturing. It could be advanced manufacturing such as additive manufacturing. So basic thing of this friction welding technology or the plastic welding technology is that heat generation at the interface of the tool and the substrate. So there are three different type of technology available that is called ultrasonic welding, spin welding, and linear vibration welding. So basically that ultrasonic welding is that which has the ultrasonic vibration, and spin welding which has the spinning on the tool, and the linear vibration which has the the hammering of the tool on the substrate material. In 3D printed electronics fabrication, ultrasonic welding technology is used. Not only ultrasonic welding technology, there has been a research effort to use the thermal embedding, the thermal embedding process, which also the similar mechanism. So the main thing about this friction welding technology is that the ultrasonic thermal and frictional energy helps to incorporate or introduce the third material on the printed plastic. So major challenges of this technology is that if you deform the substrate material badly, that means that all your entire substrate material is gone. You have to print it again, and you have to make the part again. So there is a necessity of knowledge that will help to embed different type of material within the wide variety of plastic material. That could be high temperature plastic, that could be low temperature plastic, different type of plastic material. So this is the the representation of the embedding of the solid conductor to the plastic material, and then print over the solid conductor to fabricate the the wire embedded coupon. So there are significant research effort has been done in the past, or tremendous research effort has been done in the past to understand the friction welding technology. So basic thing about this technology is that the pressure, rotation, and the surface roughness. So I'm talking about this one is the spin welding here. You can see the tool is rotating with certain rotational velocity, and then you have two different part or two different dissimilar material. So due to the rotation, it generates heat at the interface, which also the friction is the main thing here. And then due to that heat generation and the deformation of the material, these two part 1 and part 2 is there fused together. Interesting thing about this technology is that you cannot, you can weld together the metal and ceramic material together using this technology. And then in case of plastic material, the plastic deformation allows the fusion of polymer chains, and certainly in the metal and ceramics is also creating the fusion bonding at the interface. So lately we can see that the similar technology has been used in additive manufacturing technology, which is known as ultrasonic additive manufacturing technology. Basically, the way it works is that you have the stationary build platform, and you have stacked sheet metal, and then if you have the ultrasonic vibration on the sheet metal, it helps, or it fuses the sheet metal together and create the solid body. So the three key parameters of this technology is the pressure, and then velocity of the horn, and then what are the frequency, the frequency of this horn that helps to the fusion bonding of this sheet metal. So two research paper I found, Bent Stucker and Sri Raman, they demonstrated that the heat generation at the interface is 30%, less than 30% of the melting of the sheet metal. So that means that if we use the aluminum and copper metal at copper sheet metal, the heat generation at the interface like maximum the 400 Kelvin, which is not even close to the melting of those type of metal. So now my question is that what are the key things that contributing to creating the fusion bonding if it is not the temperature, if it is not the melting? So that's why I'm interested to do this analysis or do this project to understand then what are the things that contributing contributing in the bonding process of different type of materials. And then lately, I think I would say recently we in WMK Center for 3D Innovation, we found that ultrasonic technology, ultrasonic welding technology can be used to embed the solid conductor on the plastic substrate. So David Spellin in 2014 demonstrated the embedding process. However, several questions or several things are still needs to study that. What are the temperature at the interface of the tool and then the substrate plastic? What is the stress condition and how much is the deformation is happening in the plastic material? And then if I don't change the process parameter or the embedding process parameters, then is this process is repeatable? So these are the questions we need to know to use this technology in different type of material, or to introduce this technology or complement this technology to different type of advanced manufacturing technology. So objective of this project, as I said, that it's not about the melting, it's about some other thermomechanical phenomena or thermophysical phenomena. That's what I would like to understand. So to meet so the goal of this project is to people are using this technology to fabricate 3D electronics. So I thought that understanding of the welding process will help them to predict the material limitation in terms of temperature, deformation, the stress, this sort of parameters. So to know that all those information, to have all those information, I said the research objectives that must be completed in 3 different ways. That I have to set a simplified geometry that could be used to analyze the friction welding, or the similar to the friction welding, or the embedding process. And then it has to be the time dependent and thermophysical analysis. That means that I can state in different way that one of the objective is that I want to see that what are the the change in the parameters if I use the time dependent, if I want to see that time dependency, and certainly the explanation of the results to determine the materials limitation. So these are the objectives I would like to accomplish throughout this project. So you can see that I've been working on embedding of carbon fiber on the plastic substrate. So to study the thermophysical behavior of the friction embedding process, I use a horn, ultrasonic horn, that travel over the plastic substrate. And then as the representative of the real embedding process, a simplified geometry of the horn and substrate can be used. Only the horn and the substrate and setting up all the boundary condition. You can see that this is the horn tip, and this is the embedding fiber, which is the carbon fiber in this case, and this is the plastic substrate. And the simplified geometry, I choose that symmetric geometry and simplified geometry. I choose that if I have the substrate material, and then on the top of that I have the horn, and I can set up all the boundary condition, necessary boundary condition. So I'm doing for this project, I did the transient time dependent analysis, right? So to understand the time dependence analysis, or to understand the temperature behavior, I have to define some thermal properties of the material. It's because of in transient structural analysis, they don't have the the analysis setup doesn't have the thermal properties. So I defined the thermal properties of the material. Basically, I found this this code or the ID from the ANSYS help. And then just a little bit about the geometry. The thickness width of the plastic substrate is 10 millimeter, and the length I choose is 20 millimeter, and then the diameter of the radius of the horn is the 5 millimeter, and then thickness of the substrate material is 2 millimeter, and the thickness of the horn is the 2 millimeter. Again, it's a very simplified geometry of the real ultrasonic embedding process, or the friction embedding process. So let's talk about the boundary condition. So in boundary condition, I will walk you through all the boundary condition, and right here in the meshing, transient analysis, all sorts of information. So before that, I already implemented the in my model from design modeler. Once I did the design in the design modeler, I imported the geometry to the modeler, and then in that modeler I assigned the material properties like as in the previous slide. And then in the connection type, I have to define what type of connection I'm using. So it's a frictional analysis, right? So I choose that the type of the connection is that the frictional, and then the frictional coefficient is varied, but in this case you can see that 0.2, but I changed the frictional coefficient from 0.2 to 0.5 as as I found this paper, Siraman et al. 2011. They did the analysis from 0.2 to 0.5 frictional factor. And then I use the augmented Lagrange formula, formulation to convert it, relatively easily. And then I use the update stiffness in each iteration, so then it helps me to converse. And another important thing about this contact is that it's a transient structural. It doesn't really have the temperature information, so I have to put that information in the user defined command, or the command window. I have to put this information that which I found in the ANSYS help again, that is defining the elements, and that is defining the condition at the interface and calling the nodes to implement the thermal condition. And then another boundary condition is that I use the joint. So basically my substrate is held stationary, right? And then this horn is moving, or it has the translation. So to implement the fixed support at the bottom, I use the body ground option, and I choose the fixed, and I fix this body. I fix the bottom of this substrate. On the other hand, in the translational boundary condition, I choose the tip, and then from the body option, I found the translation of the horn, and in the later on, I gave the velocity of this horn in this direction. Another boundary condition, or in analysis setup, I had to put all the boundary conditions. So first of all, the analysis setting, I would like to talk about the analysis setting. So I use the number of steps only 2, and then I use the time dependent steps, where the initial steps is 0.2 and minimum step is 0.1, and then maximum time step is 0.3. And then I also use the stabilization I turned on the stabilization of this nonlinear control, just to make sure the damping factor is chosen as 0.1, since it's a frictional analysis. And then secondly, in the joint velocity, as I said in previous slide, that I have to put the velocity of this tip to move over the substrate material. So I choose the velocity is 5 millimeter per second, and then I choose the pressure on this top of this horn is 0.05 megapascal. I did a quick experiment on my the test setup on embedding process setup. that we usually use the 40 Newton load on from the horn. That means that 40 Newton means that if it's in terms of pressure, it's going to be 0.05 megapascal. So, and also I have to define the reference temperature or the thermal condition of this entire system, right? So the reference temperature is 22 degrees Celsius and then I had to mention that one in the command window of this transient setup. And to do the mesh optimization, or the meshing of this entire setup, I did the body sizing. So in body sizing, basically I choose both body, and then I put the size from 0.25 to 1.5. Basically I did opposite. First of all I put 1.5, and I did the I tried to calculate the number of nodes, number of elements, and then I gradually reduced the mesh size. And just to let you know that the thickness of this substrate material on the tip is the 2 millimeters, so I cannot go more than that, right? So yes, I did the meshing. I changed the mesh size, varied the mesh size from 1.5 to 0.25. So one of the mesh optimization or the mesh convergence criteria was that the stress. So what I did, I changed the mesh size. You can see that from I reduced the mesh size, and then I calculated the, or I tried to get the number of elements, and I got the stress. I collected the stress value, von Mises stress value. So I can see that at around 0.5 millimeter mesh size, it's pretty stable, and then suddenly it's jumped on the stress value. So therefore, for the best result, I choose 0.5 millimeter the mesh size. And then now in the simulation, or the result in this simulation, I found that in transient structural analysis, if I choose the friction factor, just to let you know that I would like to mention here is that I choose the friction factor for this analysis, or this graph is 0.5 at the interface. So the stress at the contact interface, transient structural analysis is telling me that stress at the contact interface and the maximum stress at the tip of the horn is that 183.73 kilopascal. So I did with the same boundary condition, same loading, same velocity, not velocity actually, same loading condition, and then same fixed boundary condition. I choose to do the static structural, just to see that how much stress is developing if it's not moving. So if it's not moving, I can see that the stress is a little bit lower than the transient structural analysis. So in that case, I got around 130 kilopascal. And again, the stress at the the static structural simulation is saying that the maximum stress at the interface of the tip and substrate material. And then another analysis I did is the deformation and the sliding analysis. So in transient structural analysis, I did the sliding. So sliding is basically trying to giving me the idea about that if I rotate this, or not rotate, if I move the tip of the horn in this direction, then is it trying to slide, or is it trying to penetrate, or what is happening there? So I can see that it's trying to with the 0.05 megapascal pressure, it's trying to penetrate the substrate material, which is true. With that large amount of pressure, the tool always try to penetrate the specimen, since it's a polyamide, is it's nylon, it's not that hard material, or it's stiff material, it's not that stiff material. So in the static, to understand the deformation behavior, I also did the static analysis, and then static analysis, I can see that really the material is deforming here. And then certainly one of the thing I was trying to understand that, okay, what if what if people use hammering loading, that is continuously hammering this the substrate, and then that hammering is ultimately softening the material, and then softening material means that you can introduce third material right away, and then embedding, introduce the embedding technology here. And then another objective of my this project is that to analyze the heat generation. That means that at the interface, due to the friction, is there any heat generation, or how much is that heat generation, or what are the effect of that heat generation. So for my simulation, since I didn't really choose the vibrational load, it's just a simple one directional load, and that simple load is not it's not really simulating the heat generation. It's because of the tool is moving on the surface with relatively small velocity, and they're just simply moving a tip on the substrate will not gonna generate the heat So that's why we can see that there is not really a big change in the temperature, which is basically 21.99 to 22 degrees Celsius. It's the pretty much the same temperature. So another important thing I would like to mention here, that all this analysis I did with varying I changed the free coefficient of friction and then did the analysis. So for example, I tried to present here the stress of von Mises stress of the substrate material with von Mises stress of the substrate material right at the interface, that changing the coefficient of friction. So I can see that changing of coefficient friction is not really it's not really a big of an issue, but because of the loading nature, so it's a simple loading, and the loading is not really hammering loading or ultrasonic loading. That's why the changing of the coefficient of friction is not really impactful to the stress. So in this slide, I would like to mention several things. One of them is that stress analysis. I did the stress analysis, not only stress, I did stress deformation and then temperature analysis with different type of coefficient of friction. And then transient simulation showed the higher stress is because of its moving the tool, while the stationary load is just putting on the only one the point of the substrate in the structural analysis. And then in this transient analysis, I noticed that the sliding is happening, while the that sliding could be that it's trying to penetrate the horn tip, or the horn tip is trying to penetrate the specimen. So one important thing about this simulation is that, or this analysis, is that temperature was not accurate. As I mentioned in the previous slide, that I have to define the temperature at the interface or the thermal condition of the material. So the definition or the the assignment of those temperature value was not accurate to all the noted value. So, but at the end, my conclusion, or my findings, is that it's not about the temperature, but certainly there is something that is playing vital role, and that is and those are the stress and the plastic deformation on the plastic material that is basically helping the embedding process. And also it verified by the past literature review, as I mentioned in the background slides, that it's not about the melting, but it's about the softening the material or the plastic deformation that is really allowing the third material to embed within the plastic substrate. So for this simulation, I use the polyamide material, which is not really a best material in practice. In the ANSYS software, it is possible to design the material, but I choose built-in material to get the accurate and the material properties. That's why I choose the polyamide, which already all the material information is available there. And then temperature field at the interface was not defined with the nodes. So yeah, that could be something that is not really simulating the temperature at the interface, or the changing the temperature at the interface. Another thing is that the 3D transient simulation encountered errors in the temp definition. That means that temperature in each of the nodes or each of the elements, and that's why probably it's not giving me the significant rise in the temperature. Or or maybe the loading condition. So initial thermal load impacts the solution, impacts the simulation. So if I change the temperature of the substrate material or the inter environment, then certainly it will gonna change the impact the simulation result. So one of the thing I would like to mention is that from my simulation, I just simply put the pressure, or the force from pressure from this tip, and then moving this tip around and over the substrate, and the substrate was held as a fixed support at the bottom. So in reality, if we put like vibration, or the vibrational load on this tip, then it will gonna hammer the substrate material, and that hammering would help to deform the substrate material right here, or softening the substrate material right here. And then this velocity with the certain frictional values, frictional coefficient at the interface, would help to generate the heat at the interface, and that will eventually help to bonding the third material within this plastic material. So at the end of this the presentation, I would like to mention several things. One is that to understand the plastic welding using the friction, using the friction at the interface, simulation was performed. Thermomechanical simulation were done in time dependent and time independent as well, just to compare the result and what effect of the time dependency. And then stress analysis showed the significant amount of stress generated at the tool and substrate, but there is no temperature change at the due to the loading nature. Since the velocity is relatively small, that's why it's not really generating heat at the interface of the substrate and the tip. And then another thing, I investigated that frictional coefficient changing, it's not really contributing in all cases, but it's contributing towards the stress in transient analysis. But although it's very small, it's not that really big difference between the 0.5 to 0.2. And then the embedding process is accomplished due to the plastic deformation, not the heat. So that means that I was trying to verify this information, that it's not about the melting, but it's about the plastic deformation of the substrate material right under the tip. So in future, it is possible to introduce the vibrational load to generate the heat, or at the interface, and visualize that how much heat is generating at that interface, and due to that heat or due to the temperature, how the material is softening or how the material is deforming. This sort of information certainly we can gather in the future. And then we have to use relatively smaller time step to assign the vibrational load, and this is a really important thing about the transient analysis, that setting up the right time steps to determine the effect of the time dependency of the entire simulation. And lastly, I would like to mention that this course is it's a course-based project. Throughout the semester, we learned a lot about the ANSYS. I was not really a good user of ANSYS, but using this, from this coursework, I got the hands-on experience on the ANSYS, and I was able to simulate this one. And then certainly there is some limitation on this simulation, but in future, I'm looking forward to gain more knowledge on this type of analysis, and then certainly incorporate different type of boundary condition to simulate the real life the embedding process. And then I would like to thank you my professor for this coursework, is that Dr. Kelvin Stewart. Thank you, Professor, for your tremendous support, and then you really helped us a lot to give the theoretical background, and then the instruction of performing the analysis, performing the simulation in the ANSYS. So in case again, if you need any contact information from me, or if you want to learn more about this simulation, or in future, here is my contact information, and again my little bio here. I hope you enjoyed this simulation, and I would like to thank you everyone, all the viewers, and that's all for today. If you have any questions, certainly please reach out to this email. I would try my best to come up with the answer to your question. And yeah, till then, I'm wishing everybody good health, and thank you again.